So which velocity do we use here in delta y equals v delta t? Well, actually, we really only have one velocity right this second, but it's the velocity of the swimmer relative to the ground. We want to know how long it takes the swimmer to go a certain distance relative to the ground. So we need to know how fast they're swimming relative to the ground. In this case, they're swimming in the y direction at 1 meter per second. So we can go ahead and plug in that this is v of the swimmer relative to the ground in the y direction times delta t. Because delta y is in the y direction, right? So the velocity of the swimmer relative to the ground has to be in the y direction. Otherwise, this vector equation doesn't work. This is a vector equation. In this case, the swimmer is swimming in the y direction at 1 meter per second. So we have got, here, let me just go to a new page. So we've got delta y equals 1 meter per second in the y direction times delta t. Ooh, delta y is plus 50 meters in the y direction. So that's 1 meter per second in the y direction times delta t. So therefore, delta t equals, right, we can see that delta t, or do the division and see that delta t must equal 50 seconds. Time is not a vector, right? It's a scalar that is multiplying the 1 meter per second. So the time is a scalar that multiplies the 1 meter per second in the j direction to give 50 meters in the j direction. So this works out. It's a scalar multiplying by a vector to give a vector. So you get delta t equals 50 seconds. So now what if the river is flowing? Let's go back and have the river be flowing. Whoops, don't worry about that. That was just notes to myself because there was some time between when the phone rang and when I actually did the rest of this. So now let me undo some of this and just let's add in the river flowing. And we'll still ask the same question. Oops, no, I didn't want to undo all that. All right. So what I wanted to, oh, hold on a second. Okay, there we go. So now let's say that the velocity of the water relative to the ground is 2 meters per second. But the swimmer is still swimming across the river. So let's say the swimmer is heading straight across the river, but the water is carrying the swimmer downstream. So what direction does the swimmer actually go in, right? If the swimmer is trying to, let me find a different color. If the swimmer is trying to go in this direction, swimming relative to the water, but the water is pushing the swimmer this direction, what direction does the swimmer actually go? The swimmer actually goes in that direction. Again, the first vector was the swimmer relative to the water. The second vector was the water relative to the ground. And the sum vector is the swimmer relative to the ground, just like we have down here. Okay, so we now ask, in this case, how long does it take the swimmer to cross the river? Well, there's a couple of ways to look at this. But really what I want to get at is what velocity do we use in here? Because we now have three velocities. We have the velocity of the swimmer relative to the water, and the velocity of the water relative to the ground, and the velocity of the swimmer relative to the ground. And you say, we need to use the velocity of the swimmer relative to the ground. Well, that's not true because I have here delta y. That's the distance that the swimmer is going in the y direction. What does the velocity of the water relative to the ground do? How does it change the problem? Right, so the swimmer is trying to swim, I'm going to use the highlighter. The swimmer is trying to swim across the river, but the swimmer is being pulled down river by the current. So what is the result of the water flowing? The result is it just makes the swimmer end up further downstream. So the swimmer is going to have a displacement in the x direction and a displacement in the y direction. So there's going to be a y displacement across the river, and there's going to be an x displacement downstream. So the result of the swimmer being pushed downstream is not that the water is not pushing him toward the other shore or away from the other shore. The swimmer is still going actually 1 meter per second relative to the river. The swimmer is going 1 meter per second in the y direction relative to the shore. The result of the water is that it's pulling him down further. So there's two ways to look at this. One is to just break up the motion in the x direction and the y direction. And so we can actually go ahead and say, let me figure out how to go to a new screen here. So we can say in the y direction, the swimmer is going 50 meters. 50 meters. That's the x direction. 50 meters in the y direction. And in the y direction, the swimmer is still swimming relative to the shore. The swimmer is still swimming, what was it? The swimmer is still swimming relative to the shore, 1 meter per second. You say, but wait, that's relative to the water. But that's also relative to the shore because the water is not pushing him in the direction of the y, in the y direction. So that's the swimmer's velocity relative to the water in the y direction. It's also the swimmer's velocity relative to the shore in the y direction. So we can say that, and we can say, okay, so therefore, delta y equals v sub y delta t, and plug in, and you find, okay, delta t equals 50 seconds. And again, just to be clear, I say, so what is the effect of v sub x? Well, v sub x, let me pause for a second. I went ahead and put vector signs on all the vector quantities. What's the effect of the velocity of the water relative to the ground traveling at plus 2 meters per second in the I direction? Well, it's going to pull the swimmer relative to the ground at plus 2 meters per second in the I direction. Therefore, the swimmer relative to the ground in the x direction, and I guess I didn't, for the y direction, I just put v sub y, but that was the swimmer relative to the ground in the y direction. V sub sg in the x direction is plus 2 meters per second I. And we say, okay, so what's the effect? Well, the effect is it's going to pull him downstream. Delta x equals v sub x times delta t. And v sub x being the velocity of the swimmer relative to the ground in the x direction, which is what we just wrote. And what is delta x? Well, it's going to be 2 meters per second in the I direction. And what is t? Well, we found it took 50 seconds to get across the stream. So still going to take, the swimmer is going to be pulled downstream for 50 seconds. So what's the answer? It's plus 100 meters in the x direction. So the swimmer is going to be pulled downstream, right, 100 meters in the x direction, while the swimmer goes across 50 meters in the y direction. So you can see what we've done here is we've broken the motion up into components. We break the motion into components. And notice, this is what's really important, is that the motion in the x direction does not affect the motion in the y direction. We say the motion in the x direction is independent of the motion in the y direction. You might say, well, how do I know that? That doesn't seem obvious. Well, I'll do a demonstration in a second that shows it. It's not a proof. But if you think about the problem that we just solved, it makes sense that the x direction is simply pulling him downstream, not pulling him across the stream. So his motion across the stream is still the same. But we can look at this in a different way. We can say, okay, well, let's just, if you don't believe me, let's go ahead and do the two-dimensional motion. So hold on. So let's go ahead and do the two-dimensional motion and not break it up into the components the way that we just did it, which really is the best way to do it. But let's just think about, let me go ahead and redraw that the swimmer is going, whoops, that's an eraser. The swimmer is going 1 meter per second in that direction. The swimmer is going 2 meters per second in that direction. These are the velocity vectors. I'm just redrawing them. And so the resultant vector for the swimmer's velocity is in this direction, right? So this is the velocity of the swimmer relative to the water, and the velocity of the water relative to the ground. And so you add those two to get the velocity of the swimmer relative to the ground. That's the bottom equation right here. And so I'm going to write that out as the velocity of the swimmer relative to the ground is the velocity of the swimmer relative to the water, which is plus 1 meters per second in the j direction, plus the velocity of the water relative to the ground, which is plus 2 meters per second in the I direction. So the velocity of the swimmer relative to the ground, this vector here is this vector here, right? So that's the vector. It's got two components, which we already knew, of 1 meter per second in the y and 2 meters per second in the x. And so we can actually write that out in magnitude and direction form, if you really like. So the magnitude, given by the square root of the sum of the square root of the components, because it's a right triangle, is 2.24 meters per second. And the angle, it depends on which angle we want, but let's just say that we talk about the angle from the original direction being straight across, that's theta. So the angle, we can write that as the inverse tangent of opposite over adjacent. VWG is, so that's 2 over 1. So the angle is 63.4 degrees downstream from the original direction, or in the plus counterclockwise from the plus y-axis. But remember, you've got to do that, right? You've got to give me relative to what axis. So I'll just say CCW from plus y. Sorry, I didn't leave a lot of space there. So we've now got the swimmer going in the direction shown in the arrow here with the velocity shown. And let me just ask the question, how far will the swimmer swim in 50 seconds? So how far will the swimmer swim in 50 seconds? I don't remember if it was a he or a she. Let's just say she, go in 50 seconds. Well, the swimmer is going to swim 50 times 2.24. Okay, it's still a one-dimensional problem, because now we're just saying that the swimmer is swimming along this line, and they're going 2.24 meters per second along that line. And I'm just saying in 50 seconds, how far do they go? So they go 112 meters. So what I want to say is, if they go 112 meters along that line, then how far have they gone in the y direction and how far have they gone in the x direction, right? Delta y and delta x. And that's simply drawing a triangle, right? We're saying that they've gone 112 meters, and we want to know what is the x and what is the y if this angle is 63.4 degrees. So this is delta d, or the resultant vector, and so delta x, we can say that sine of 63.4 degrees is equal to opposite over adjacent, delta x over 112 meters. So therefore, delta x is equal to 100 meters. And we can do the same thing for delta y. Here, trying to leave enough space. Cosine of 63.4 degrees equals delta y over the hypotenuse, 112 meters. And what do you think delta y is? Delta y is plus 50 meters. So what I'm showing here is that if we do the two-dimensional motion, if we take into account both components at the same time, and we say, okay, the swimmer goes 50 seconds, the swimmer's going to go, we can figure out that the swimmer's going to go 100 meters downstream and 50 meters across, which is exactly what we got by breaking it up into components and treating the two components separately. We break motion, whoops, that was not what I meant to do. We break motion into components, motion in the x direction is independent of motion in the y direction, and we can just solve for the motion in the two independent directions. Okay, so what we just spent time doing was both velocity addition, right? We did some velocity addition. We figured out how to figure out what the velocity of how to add velocities when one thing is moving relative to another. That's relative motion. That's an important concept, this relative motion that we discussed in the last video. Adding velocities and the independence of motion in perpendicular directions in the x and y, and z, of course, direction. Independence of motion, perpendicular directions. So we're going to really delve into the 2D chapter now. But in the 2D chapter, all we're really going to do is we're going to take every problem and we're going to break it up into two one-dimensional problems, right? X direction, Y direction, or three one-dimensional problems, X direction, Y direction, Z direction, or four one-dimensional problems if we lived in four-dimensional space. But we don't. Really. We'll pretend we don't anyway. Yeah, so the 2D chapter really is just a repeat of the 1D chapter, just being able to break the motion up into two different perpendicular directions. So, see you soon.